Welcome to Optical Fiber Communication Laboratory Manual. In today's session, we will discuss Practical 9. Request to like, subscribe, press bell icon, share and comment. This is the sample of certificate. Index. In earlier video, we have discussed example related to optical fiber waveguide, transmission characteristic of optical fibers and cables, optical fiber connection, joint, coupler and isolator, optical source, the laser, optical source, LED, optical detector and digital transmission system. In today's laboratory, we will discuss Scilab code for given example of optical amplifiers. Practical 9. Optical amplifier. Aim to write a Scilab code for given examples of optical fire. Software Scilab with version 6.1.0. Theory: a device which amplifies an optical signal directly without converting it to an electrical signal is known as an optical amplifier. Optical amplifier is an important device used for optical communication and laser physics. Optical amplifiers are always installed at those places where optical signals are weak and need to be magnified. Need of optical amplifier. First, transmit a signal over a long distance greater than 100 km. Optical amplifiers are required. Second, compensate attenuation losses. And third, boost up the power level of many light wave signals. Working principle of optical amplifier. The optical amplifiers amplify the incident light or power amplification by using a process of stimulated emission of radiation or an optical power transfer process. Stimulated emission. Stimulated emission takes place when an external signal photon causes an excited electron at a higher energy level to drop back to its ground state. Photon emitted by the electron while dropping back and the incident signal photon has the same energy, like same wavelength. The stimulated emission can occur only if there is a population inversion of carriers. Population inversion of carrier implies that the number of electrons in excited is higher as compared to number of ground state. Application of optical amplifier. The general four possible application of optical amplifier: first, A. Inline amplifier to increase transmission distance. B. Preamplifier to improve receiver sensitivity. C. Booster of transmitted power, and option D, booster of signal level in a local area network. Figure 9.A represents general application of optical amplifier with A, B, C and D as option discussed earlier. Types of an optical amplifier. Figure 9.2 indicate types of an optical amplifier with semiconductor optical amplifier, erbium doped fiber amplifier, Raman amplifier and wideband optical amplifier. Semiconductor optical amplifier. Figure 9.3 indicates semiconductor optical amplifier with optical input signal, fiber to fiber coupler, active medium, pump source and amplified optical output. The photon density is given by n suffix ph equal to ps divided by vg hv wd. Equation 9.1, where PS indicate power of optical signal, Vg indicate group velocity, HV indicate energy of photons, W indicate width of optical amplifier and D indicate thickness of optical amplifier. The pumping rate for the SOA indicate Rp is equal to J of T divided by Qd, equation 9.2, where J of T is the injection current density, D the thickness of active layer. And the zero signal gain is defined by G suffix 0 is equal to A to J by Qd minus NTH by tau R, equation 9.3, where this phi complement factor A is a gain constant which depends on the optical frequency V, J by Qd is a pumping rate and TH threshold carrier density, Tau suffix r is a combined time constant coming from spontaneous emission and cadence recombination mechanism. Advantage: the size of semiconductor optical amplifier is small as compared to EDF. These are less expensive and can be incorporated with semiconductor laser, modulator, etc. Disadvantage: higher noise and lower gain, dependence on polarization, and higher non-linearity. Second, erbium doped fiber amplifier. Architecture and configuration of EDFA is shown in figure, with co-directional pumping, with signal in, tap coupler, optical isolator, wavelet, selective coupler, pump laser, optical isolator and tap coupler, and signal out. Figure 9.4b indicate counter directional pumping, with signal in and signal out with a tap coupler, optical isolator, wavelet, selective coupler, optical isolator and tap coupler. Then 9.4c indicate dual pumping, both the side, tap coupler, optical isolator, wavelet, selective coupler, both the side, and signal in, signal out with pump in both direction. The maximum input power PS in for EDF is given by PS in less than or equal to lambda P divided by lambda S P PPN G minus 1, and maximum output power PS out for EDF is given by PS out maximum is equal to PS in maximum plus lambda P by lambda S P PN. Equation 9.5, where lambda suffix P is a pump wavelength, lambda S is a signal wavelength, G is amplifier gain, P suffix Pn is the input pump power. Advantage: high pump power utilization greater than 50%. High gain and low noise can be used as a power amplifier. Disadvantage: large size cannot be integrated with other semiconductor device. Third, Raman optical amplifier. Figure 9.5 indicates Raman amplifier with input and output with the transmission fiber, monitoring photodiode, WDM coupler, GFF monitoring photodiode, and input from the pump laser. Advantage: wide gain bandwidth, low noise, distributed amplifier within the transmission fiber. Disadvantage: high pump power requirement, low efficiency and high cost, and low gain. Let's try to solve the example related to this chapter. Question 1. Consider an indium gallium arsenide phosphide SOA with W is equal to 5 micrometer and D is equal to 0.5 micrometer. Given that Vg is equal to 2 into 10 raised to 8 meter per second, if a 1 microwatt optical signal at 50-50 nanometer enters the device, then determine the photon density value. Good. So given data as per 1, use equation 9.1 to solve this particular example. So clear for clear variable browser, CLC for clear console, and close for if any other file is open or not, then it can be closed. Then VG, H VG is given, H and C is the standard value, H equal to 6.625 e raised to minus 35, Planck constant, C 3 raised to 8, free space velocity in meter per second, lambda is given 1550 e raised to minus 9, operating wavelength, V is equal to C by lambda, frequency in hertz, W is equal to 5 into minus 6, width of optical amplifier meter, D is equal to 0.5 e raised to minus 6, thickness of optical amplifier meter, PS equal to 1 into 10 minus 6, optical signal of power, and then we use equation 9.1 for calculation of photon density. So NPH equal to PS divided by VG HV WD. And finally displaying the result with the help of this function NPH, the photon density in the photons per cubic meter. Let's try to run this code in the Scilab. So clear, CLC and close function are used to clear the variable browser, clear the console window, and close the any other opening file. VG as per given data, H and C is the standard value, lambda is given, we have to use V for calculation of frequency in hertz, WD is given, then we have to use NPH as per equation 9.1 for calculation, and finally displaying the result with the help of this command. Then execute this code. The result is 1.56 d raised to 16. The photon density in photon per cubic meter is this particular value. So this is the answer of this particular example. Same is printed. Question 2. Consider the following parameter for a 3000 nanometer indium gallium arsenide phosphide SOA with symbol parameter value. W is active area width 3 micrometer, D is equal to active area thickness 0.3 micrometer, L amplifier length 500 micrometer, mu is a confinement factor 0.3, 2R is equal to time constant 1 nanosecond, A is a gain coefficient 2 into 10 raised to minus 20 meters square, NTA threshold density 1 into 10 raised to 24 meter Inverse Q. If a 100 milliampere bias current is applied to the device, then what is the pumping rate? And second, determine the zero signal gain value. So solving this particular example, we have to use equation 9.2 and 9.3, then clear CLC close, then this is the given data I, W, L, D, Q as per standard value. So I is equal to 100 into minus 3, bias current in amplifier, W is equal to 3 into minus 6, active area width in meter, L is equal to 500 to minus 6, amplifier length in the meter, D is equal to 0.3 to minus 6, active area thickness in the meter, Q is equal to 1.602 to minus 90, charge in coulomb, and then we have to use equation 9.2, that is R is equal to I divided by Q D WL. Then this is the pumping rate in electrons per hour, and then we have to calculate once again the zero signal gain. So for that we have to use equation 9.3. So tau is given, that is 0.3, the confinement factor, then A is 2 into 10 minus 20, the gain coefficient in square meter, J is equal to I by WL, the bias current density amplifier square meter, and that is equal to threshold density per cubic meter, 1 into 10 to 4. Tau is equal to 1 into minus 9, the time constant in second, and then we use equation 9.3 is a G of 0, that is equal to tau into A into tau R into J divided by QD and divided by tau R. So finally displaying the result with the help of this function. So let's try to run this code in the Scilab. Okay, so we have to just use equation 9.2 and 9.3 to solve this equation, question 2, and display the result with the help of this function. Let's execute this code. So we can check that the pumping rate in electrons per cubic meter is 1.38 D plus 33, and the zero signal gain per centimeter is 23.22, and the same result are printed in this particular document. Now question 3. Consider an ADFA being pumped at 980 nanometer with a 30 milliwatt pump power. If the gain at 50 nanometer is 20 dB, what are the values of maximum input and maximum output power? Let's try to run this code in this example in the Scilab. First we understand the code that as per given data we have to use equation 9.4 and 9.5 to solve this particular example. Then clear CLC close we have to use, then lambda P, lambda S as per given data, then PP in and G, that is the gain. Then we have to use this equation 9.4, that is the PS in lambda P divided by lambda S into PP in divided by G minus 1, that is the maximum input power, and the maximum output power is equal to PS out equal to PS in plus lambda P divided by lambda S into PP in. So displaying the result with the help of this command. So let's try to run this code in the Scilab. Execute this, save and execute. Okay, so the maximum input power in microwatt is a PS in equal to 191.59. Then maximum output power in micro milliwatt is a PS out, that is equal to 19.1593, and the maximum output power in the dBm, that is equal to 12.823804. So that is the answer of this particular example. Same is printed in this document. Conclusion. This experiment is about to know what is optical amplifier. This experiment defines the need of optical amplifier, its feature, different types of optical amplifier and application of it. This experiment also demonstrates mathematical equation with the example for digital transmission system with the help of Scilab. Note, demonstrated examples are given in Optical Fiber Communication Gerd-Kaiser McGraw-Hill 3rd edition book. Example numbers are 11.1, 11.2 and 11.3. Thank you.